Recording in progress. Recording in progress.
Hey, good evening. It is Wednesday, February 14th, I believe, and this is a recorded lecture for ECE 430, and we are looking at chapter 9. So we have already done with chapter 5, 6, 7 review, and we went through chapter 8 with the basic building blocks of amplifier circuits. So today we're going to start chapter 9 to look at the differential and the multi-stage amplifiers. Just give me 1 second. I'm going to bring up the class slides of chapter 9. We're going to start right away. It's going to take a minute to load the slides. So here, let me go start the share screen. Okay. Yeah. Now, I hope you guys can see my screen. So in chapter 9, we'll focus on differential and multi-stage amplifiers. This is going to be a total of 3 to 4 lectures, depending on how you guys follow the lecture contents. And basically, there are 3 basic topics, 3 areas. In the first lecture, we're going to cover the MOSFET amplifier. And in the second lecture, we're going to talk about the differential amplifier using BJTs. In our last lecture, we're going to talk about the multi-stage amplifiers. And multi-stage amplifiers is basically used to design like op amps, things like that. We are going to discuss one by one, and as I said in part 1, we're going to focus on most differential amplifiers. But before that, let me bring up this differential amplifier circuit. So in this circuit, you can see we have 2 MOSFETs. They're both NMOS. At the gate of each MOSFET, there is a voltage input connected, which is VG1 and VG2. So they are both connected. At the source, there is current source that's connected to the source of each MOSFET. And then at the drain, there's a resistance RD connect to the voltage source. So this is a okay. Give me 1 second. I'm going to bring this up. Hold on. Let me make sure I have my sound. Yes, I have. Okay, that sounds good. I have my voice recorded, hopefully, because we did lose voice for a few times in the past. So hopefully this will be good. Let's see. So this here, we can do a couple of things with the equivalent circuit. Well, first of all, we can do, for example, DC biasing analysis. And then we can do, so from the DC biasing analysis, we can find out the, say, the gain from that point. So let's start maybe as a first step to do the DC analysis. So for DC analysis, as you already know, the voltage source, like the input VG1, they're both input, the voltage source, so they become a short circuit. So which means that both of these MOSFETs, the gates of both MOSFETs are going to be grounded. And the source is connected to a constant current source, and each one of them is going to conduct like half of the current. So for that purpose, I'm going to draw this in a very particular way so that you understand why this DC circuit is going to look like that. So start with the drain resistance and the MOSFET gate grounded, and then for this part, we're gonna drain the circuit. Each is gonna put half of the current, and the bottom is connected with SS. The top is connected with ED, and it's RD, and RD they're symmetrical, and then we get the output is between the gate of MOSFET 2, Q2, and MOSFET Q1. Okay. So now you know that if in the DC mode, the current is already given. So therefore, we can easily calculate let's calculate VD1 and VD2. So we know that VD1 is going to be VDD minus RD times 1/2 I. And VD2 is going to be the same thing, RD times 1/2 I. So what is VO in this case? So VO is going to be that VD2 minus VD1, which is 0. So that's exactly what we have, what we expected. Now, of course, the current source is something like we learned from chapter 8, which is made up of MOSFETs, different MOSFETs. They look like the current mirrors or current sources, however you design that circuit. But if if we're able to know current, we should be able to find the gain of the circuit, which like the GM. We can find it. There's equation here. I don't remember exactly how the equations be written, but you should be able to find that the gain for the GM. The other thing that we are going to look at is, well, the previous one was connected to ground. So what happens if, let's put it this way. So I need to figure out how to calculate GM. In this case, there's the equation, of course, we have to find out. Well, we learned this earlier. It's the equation, so you guys can write down in a piece of paper, so you don't have to memorize it either for your final exam. But in this particular circuit, what we wanted to also to understand is that what happens if the gate is not connected to ground, like if each of them is connected to a voltage. And in this case, we connect both gate with the same voltage. Because they're same, we call it COM. They're common, so they are same. So this is called common mode. When we say common mode, which means the gates are connected to the same voltage. So what happens with the same voltage? Now because the voltage at the gate is connected to a voltage source, which in this case is DC voltage source. It does not change. It does not change the output, because regardless of the gate voltage is connected, you still have VD1 equal to VDD minus 1/2 I times RD, which is equal to VD2. And we always equal to VD2 minus VD1. That's 0. So nothing will change. Now, of course, we have to do one thing we're careful is what is the range of VCM in this case, such that this thing is still in saturation, because that's what we want. If it's not in saturation, we'll not be able to use it as an amplifier. So we want to make sure it's in saturation. If this circuit is in saturation, we note a few things. the first thing is that VGS has to be larger than VT. Now, in this case, because VGS is equal to VCM minus VS, and VS can be anything because VS is the what in this case VS is really equal to here we call it VCS is equal to VCS minus VSS, which means VSS is equal to VS is equal to minus VSS plus VCS. So that's what we have. So VCS can be quite a small value, which in this case could be negative or could be positive, depending on what VCS is. But the second condition, this VGS equal to VT can only make sure it's not in cutoff, but it could still be in triode, it could still be in saturation. So in order to be in saturation, we have to make sure that VDS has to be larger than VGS minus VT. Sometimes it's called overdrive voltage, which is VO. Sometimes we call that. This VO is different from in the future, we call VO output. This is like overdrive voltage, right? So if we have to maintain VGS larger than VT and also VDS larger than VGS minus VT, now if we replace this VGS with VCM minus VS minus VT, and we can get right away that VS equal to so this has to be larger than VO. So we can get VS has to be less than, in this case, it has less than VCM minus VS minus VO. Right? So VGS is VCM minus VS. So that's correct. So we got this equation over here, which if you look at this equation here is almost the same, but simply they replace VGS to VS minus VO here to get this equation. So in the sense that VDS in this case, you can also express VDS equal to, you can also express VDS equal to VD1 minus VS, and that has to be larger than VO. So that VD1, right, VD1 is already calculated along this equation over here. So that's how we want to make sure that this common mode input and output, they're going to be eventually make sure it is in the saturation mode. So this example in the book, and then we can look at this calculations with this example. If those numbers are given, and we can find out what is the output and what is the voltage at a different node when the input is connected to ground, or when the input is connected to a common mode input, which is some sort of DC value. So in this example, the current is given, I is 0.4. So since I is 0.4 milliamps, so 1/2 I is going to be 0.2 milliamps. And we can easily calculate VD1, and they're same as VD2 equal to VDD minus 1/2 I times RD. VDD is 1.5 minus milliamps times 2.5K. So in this case, 0.2 times 2.5, which is 0.5. So you got VD1 equal to exactly 1 volt. Since this is 1 volt, now we can calculate. So VD1 and VD2 are 1 volt, and from VG, now VG is 0, and VG1, VG2 they're both 0. So we can calculate VGS is VG minus VS equal to minus VS, right? So this is what we get VGS. And we can calculate this I equal to, or ID equal to 1/2 KWOL times VGS minus VT squared. Since VT is given, this VGS, VT is given, K and WL, they are both given. So we can calculate this, plugging K, WL, and VT, we can calculate VGS to be 0.82 volts. So this is what we get from the example. So we got VGS 0.8 volt, 0.82 volts. Once we got this 0.2 volts, we can get the voltage at the also at the source. So let's do another calculation to find out what the VS is. Since we know that VGS equation here, VGS is equal to minus VS, so therefore we have VS is minus VGS is minus 0.82 volts. So we solve basically the problem. So I also want to go one step further, called VCS, the current source voltage. So because if you look at, if we use VS minus VSS, that's going to equal to VCS. Therefore, VCS equal to VS is minus 0.82 minus 1.5, which gives you 0.68 volts. So that's the VCS voltage, the voltage across the current source. So this is a fairly simple example for the common mode. So the next step is that we're going to look at what happens when the gate voltage is not zero. So when the gate voltage, of course, is zero, we know that the output, now of course I need to write down here is VD1 minus VD2, or VD2 minus VD1 in this case, equal to VO equal to 0. Let's make this a little bit of correction here so we don't get confused. What happened here? Okay, so this thing is not working properly. So this is VS minus VGS, and this is VCS equal to, and then VD2 minus VD1 equal to VO equal to 0. So we got everything we need on the circuit for the common mode input when the gate voltage is 0. When the gate voltage is not 0, we need now to recalculate everything, but not likely. We don't actually have to calculate everything, because in this case, VG1 and VG2, because of common mode, again, this is all both connect to 1 volt, the same voltage. But since the current didn't change, the current is the same. Current is still 0.4 milliamp. So therefore, VD1 and VD2 do not change. They are both 1.5 volts minus half of the current times 2.5 kilo ohms. So it's still equal to 1.0 volt. So this is what you get for VD1 and VD2. The only difference, of course, now is VGS is different. So VGS VGS now is 1 minus VS, which because the current didn't change. So from the previous slide that we know that, let me actually do one step further instead. Because VGS, because ID didn't change, so ID equal to 1/2 KWL VGS minus VT squared. So therefore, VGS does not change. It's going to still 0.82 volts. So if VGS is the same, but VGS in this circuit is equal to VG minus VS equal to 0.82, but VG now is VGS 0.2, so VG is 1, so VG is 1, so 1 minus VS equal to 0.82, so therefore VS equal to 1 minus 0.82 equal to 0.18 volts. So this is VS now. So how about VCS? So VCS, we use the same equation, is that VCS equal to 0.18 minus 1.5. So this gives you 1.68 volts. So VCS is much bigger than it is before. So this illustrates how we can calculate the voltage of the example in the circuit. So one more step is that we're going to calculate what happens with if the voltage changes to negative. So similarly, this VD doesn't change. So VD1 and VD2 is going to be the same. We're not going to repeat the calculations, and VGS is going to be the same. We're always assuming that it is in the saturation region. So VGS is the same, 0.82 volts. Now S is going to be different because VG minus VS equal to 0.82, and VS equal to VG minus 0.82, and VG now is, in this case, is minus 0.2, minus 0.82. So we got VS equal to minus 1.02 volts. And I think this is what we get from here, 1.2 volts. And we can further calculate VCS. So VCS is going to be minus 0.102 minus 1.5. That gives you something like 0.48 volts. That's VCS. But here, I just want to do a little bit step further, is that because we assume the thing is in saturation, so we want to find out when would this thing come out of saturation that we're no longer able to use it as amplifier. Well, since we know the equation here, I want to write this equation here using a different color, is that we know that VGS has to be, so VGS has to be larger than VT. That's the first condition. And second condition is VDS has to be larger than VO, and VO is VGS minus VT. So in this example, the VT is given by, let's see, example 1. Okay, so VT is given at 0.5, and KWL is 4. So in this case, let me write this down. So KWOL is 4 and this is milliamp per volt squared, and VT is 0.5. Which is 0.5 volts. So that's the given condition. But if we need to have VDS larger than VO, so VGS in this case we already calculated based on the current. So VGS was calculated to be 0.82 volts, which means VO equal to VGS minus VT. That gives you 0.32 volts. And VDS, and how much is VDS? Well, VDS is given from VD1 minus VS. And so now we can calculate the 3 cases to see which one. Or in other case, if we do this calculation, we have to make sure that VDS is VO, VD1. VD1 is calculated to be 1 volt. And minus VS has to be larger than, this is not VO, this is VD. So it has to be larger than VDS has to be larger than 0.32 volts. So we can further find out that Vs has to be less than 1 minus 0.32 has to be less than 0.68 volts. So this is, Vs has to be less than 0.68 volts to be able to conduct in the saturation region for both of the MOSFET. So if we look at the previous example, we find that, let's go back to our previous example. Okay, so in this case, we have the grounded, we have the gate grounded, and then we have VGS, we got Vs equal to, where's Vs? So Vs is equal to here. So Vs equal to minus 0.28. Okay, that's definitely less than that. And then in the second example, we got Vs equal to 0.18, which is okay too. In the third example, we got Vs equal to minus 1.2. So in all the cases, we have this Vs less than 0.68 volts. If we want to define what is the range for VCM, because this VCM, it will bring, so VCM has a range, has a max and a mean. This VCM max and mean will bring this out of saturation or cut off. So for example, if VCM is too big, we already know that Vs is Vg, which is VCM minus 0.82. So that's what you have for Vg, which in this case, so Vg is to VCM. So if Vg is too big, and this is going to be out of saturation mode, right? So that's your VCM max. So from there we can calculate, well, Vs, because we need to calculate Vs, let's see. So Vg minus 0.82 gives you Vs. So we should be able to find VCM is so VDS is, no, we will probably do a few more steps. So VDS is VD minus Vs, and VDS has to be larger than, so VD is given as 1 minus Vs. Vs is equal to Vg minus 0.82 plus 8.2 now, so equal to 1.82 minus Vg. So VDS has to be larger than VO. VO is 0.32. So in this case, we can have 1.82 minus Vg has to be larger than 0.32. So we got a Vg has to be less than 1.82 minus 0.32. We got 1.5 volts. So this is your max VCM. Max is 1.5 volts. And the minimum of volts, of course, is that if it's too small, it's negative, 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 and we might be also bring this. We bring this out of saturation, and potentially it's going to be cut off. So if it is in cut off, we will know that this VGS has to be less than VT, and the VGS is, I said VGS, VGS less than VT, which is, or larger than VT, you know, to compare into this into either child or operation mode. And VGS equal to VCM minus Vs has to be larger than 0.5. And Vs, VCM. So then in this case, we really don't know. We really don't know Vs. Let's see, minimum 5, 2, BCS. Oh, okay. So I guess one of the things that we need to know, let's see for this given. Okay, so yes. So VCS in the example, it did give VCS mean is 0.4 volt. So this is given. So if VCS is given, so we know that Vs equal to, so in this case, we know that Vs equal to Vs equal to VCS equal to 1.5, basically VSS. So what we can do is we got Vs minus VCS equal to minus VSS equal to VCS, right? So Vs equal to V minus VCS plus VCS plus VCS. So in this case, VSS is 1.5 plus VCS minimum 0.4. So we got 1.1 minus 1.1. So this, let me rewrite this. So this should be minus 1.1 volt. Use red color to make it better color. So VCM minus Vs is larger than 0.5, and Vs, let's call it. So Vs minus VSS equal to VCS equal to larger than 0.4 volts. So Vs equal to, or has to be larger than VSS plus 0.4. And Vs is 1.5 minus 1.5, by the way, plus 0.4. That gives you minus 1.1 volt. So we plug in this one back into here. We got our VCM mean equal to Vs plus 0.5. Vs is now minus 1.1 plus 0.5. That gives you minus 0.6 volts. So this is going to make sure that the thing is not going to be in cutoff. But that's not enough, because we have to make sure that VDS is larger than, VDS has to be larger than, VGS has to be larger than VO, which is overdrive voltage. So therefore, really, we have to make sure that VDS, which now is 1 volt minus Vs, and in this case, Vs is minimum is 1.1. So 1 minus 1.1, and that has to be, that's VDS. That has to be larger than VCM minus VCM minus Vs. That's VGS, and then minus VT. So we have now VCM has to be larger than, on this side is 2.1. VCM has to be less than 1.1 with 1.1. No, wait a second, this is wrong. Let me erase the part so that we can get a pic. So we already got the minimum. So now we already got the maximum for that. So let me rewrite that so that you guys get a better picture. So let me redo the VCM max. So we know that VGS equal to VCM minus VS has to be larger than this VGS, and VD has equal to 1 volt, which is VD1. Let's go to VD1 minus VS, and this has to be larger than VO. And we know that VO is VGS, which is already given, which is VGS minus VT, 0.32 volts. So VD1 is given as 1. So now this 1 minus VS has to be larger than 0.32. Okay. 0.32. So VS has to be less than 1 plus 0.32. No, something is wrong. So VCM, VDS is equal to VD1 is 1 minus VS. No, VS. Well, VS is VGS. No, this. Sorry. We do this one. I want to make sure that I got everything is correct so that I don't confuse you guys. So VDS has to be less than that, but VS is really VS is, in this case, let's say, so VGS, so VS is equal to so VGS equal to, so CM, so VS equal to VCM minus VGS, and VGS we calculate to be 0.82, and VO is 0.32. So now we got it correct. So from this equation here, we have VS has to be less than VD1 minus VO, and VD1 is VS is last VDS VD1. Okay, so VD1 is 1. VD1 is 1 minus VO is 0.3 VGS. VDS is VD1 minus VS, and VS equal to VCM minus VGS. So VS equal to so VS equal to VD1 minus VD1 minus V. Oh no, sorry. I'm looking at the wrong thing. Well, we're finding VCM. So VCM equal to VS plus VGS. In this case, VGS is VCM minus VGS. VS from here equation here. So VS is equal to VS is from this equation. So VS equal to VD1 minus VO. So VD1 minus VO plus VGS, and VD1 is equal to 1 minus VO is 0.32 plus 0.82. Yeah, so now we got it right. So which is equal to 1.5 volts. So we see VCM max is this, and for VC mean we have to use VCS mean is equal to 0.4 volts. So here we want to find, so this is to find VCM max, and here we find VCM mean. So VCM mean is from the previous example that we have to make sure that this VGS, same equation would apply. But in this case, we have to calculate VS mean. So VS minus VSS equal to VCS. And VCS mean is 0.4, So we got Vs equal to Vss plus Vcs mean equal to 1.5 plus 0.4. That gives you minus 1.1 volt. So that's VSS given. So now we use VGS. Now we use VDS. VDS is equal to 1 minus Vs, which is 1.1, has to be larger than VO is 0.32. VDS, so now we have we 3.2. VDS has to be larger than well, no, 0.32 is not given. That's what I commented. 0.2 was given, right? So in this case, VDS is going to be equal to VDS equal to VD1 minus Vs, and this has to be larger than VO, and then and that's equal to VCM minus Vs. So we got VD1, so now we have VCM has to be less than VCM has to be less than I got a mistake somewhere. The calculation has to be that the voltage VGS, so VG minus VS, is over voltage. So VG is VCM. So VCM minus VS, so VS is minus 1.1. So VCM minus 1.1. So VCM minus 1.1 has to be then VD is VD1 minus VS. 1 minus VS has to be larger than VCM. So VD1 is 1 volt. Somewhere there was a mistake. Let me make sure that I can recover this error. So VCS, VGS equal to, oh yeah. So VGS is given at 0.82. So I apologize. I know that you guys are probably going to confuse too at some point. But the idea is that we want to make sure that we got this thing correct, right? So otherwise, we'll be all in trouble. So the VCM mean is we know that for that kind of current, VGS is already calculated to be 0.82 volts. And VGS is calculated, and VO is going to be 0.32 volts. That's VGS minus that. So we have VDS has to be larger than VO. Now VDS equal to VD1 minus Vs, and VD1 is 1. VDS is 1. So VDS is VD1 is 1 volt. So which means 0.3. There's a 32 volts. There's 32 volts. So 0.32. 0.32. Just make sure that I got this in the correct formation. So VDS equal to VD1 minus Vs, and it has to be larger than 0.32 volts. So VD1 is 1, so Vs has to be less than 1 minus 0.32 volts. So this is going to be 0.68 volts. VGS, so VGS VGS 0.2, and VG minus VS is 0.82, and VS is going to be 0. So okay, so now VS has to be large. Then now we need to find out what VCM is. So VCM, I don't have a space. So VCM equal to VS plus 0.82, right? So if VS is larger than, has to be less than 0.68, 3.1. Let me make sure I got everything correct. So VS go to, yeah, 6.82. So VCM equal to VCM equal to VS plus 0.2. So therefore, 0.2, so that's 1.5. So she can be maximum at 1.5 volts. So now, sorry, now we calculate actually is maximum voltage, not the minimum voltage. Connect the minimum voltage. I have to figure this out. I can get this down. So VCS me plus VSS plus VGS is minimum. So basically, I'm going to draw on the next slide. So basically from here, so this, I want to just, we're going to use this for small signal, but so if this VCS mean is 0.4 volts, and so this minus VSS is minus 1.5 volts, and this is 0.82 volts maximum. So the minimum VCM, so in this case, we should be able to calculate VCM is basically is 1.5 minus 1.5 plus 0.4 plus 0.82. Okay, so now we got it really. It's just going to be minus 0.28 volts. So that's the CM minimum. Because we know the VCS, so there's we don't have to really, because if VCF drops more than, has to be larger. If it drops more than 0.28, and it's not possible to maintain VCS mean, or if you maintain VCS mean, VGS can be less than 0.82. Okay, so that's how we got it. So I'm going to replace this one. So VCM mean is going to be VCM mean. So I'm going to rewrite this one, just hopefully that this is going to be. So VCM is going to be VCM. It's going to be VSS minus VSS, right? Minus VSS, yeah. Plus, so VSS plus VCS mean plus VGS. So VGS is 0.28. That's how we maintain the current, which is minus 1.5 plus 0.4 plus 0.82. So that gives you, it has to be larger than this. And equal to 0.28 volts minus 0.28 volts. So okay, so we got that correct. So far we finished all the analysis on the common mode input. And the most important part of this differential amplifier is not the common mode. Of course, it is important, but we just have to understand that the most important function is to use it as a differential amplifier. So in this case, we're going to have the circuit connected to an input. In this example, the one with the gate, the Q1 is connected to input, but the other one is connected to ground. So we want to figure out, like, how do you draw the small equivalent circuit. We already know, like from the previous example, how to calculate the DC biasing, the minimum common mode input, and the maximum common mode input. So now we have the differential input. But in this case, as I said, the input is applied all to the transistor on the left hand. The right hand transistor is grounded. We can draw the small signal equivalent circuit so that we can analyze the gain. In this case, what we're going to do is let's simply draw the equivalent circuit before we have a couple more slides to analyze. So in this case, the equivalent circuit of the left hand is something like this. The input is at the gate. So we have the gate. We call it VGS, but in this case, VGS is same as VID. And we're also going to include this, we're not going to include the RO, but we're going to include this RD in the circuit. So that's your right hand. So that's your VD1, okay? And on the left hand, we're going to draw similarly the gate, but we're going to flip. We're going to flip the circuit so that we make it easier. And one thing of course, I need to indicate once I finish this drawing is that this gate is grounded, okay? So if it's grounded, VGS2 is 0, and this is VGS2 times GM2, okay? So this is like GM1. So this is your equivalent circuit, and this is RD, so VD2. So you can possibly, from here, you can easily say, well, because VGS2 is grounded, so VGS2 is 0, so GM2 is 0. So if GM2 is 0, that the current is open circuit. So over here, basically, the current is open circuit here. When the current is open circuit here, RD2 has no current, so the voltage at VD2 is 0. So we can easily find that VD2 is 0. And VD1, we can calculate it. So VD1 is going to be minus GM times VGS times RD. And this VGS is equal to VID. So, and if we calculate, on the markup, we have VO. So in this case, we have VO equal to VD2 minus VD1 equal to GM times RD times VID. So here we can calculate the gain is VO over VID equal to basically GM times RD. So we got the gain of the circuit by simply doing the equivalent circuit. But you actually might wonder, no, that's not true, because the source is not grounded. But in the example that we draw here, we put everything at the ground. But the source is not grounded. The source has a current source, right? So this is not ground. So if the source has no ground, and the analysis could be wrong. So what are we going to do then? Well, you will figure out that this actual assumption is correct. And the reason is very simple. Yes, the source is not grounded. But if you look at the source of the two transistors, what happened? You can easily find the two sources are connected to each other. So which means if I use a blue line, I will be able to connect the source, which like the source over here, which is the source over here, they are connected. They're connected. So because they're connected, so VD2, you can see, but there's no current on the other hand. So basically, I can draw this circuit in a different equivalent circuit. Oops, I made a mistake. How do I redo it? I cannot redo it. Okay, that's fine. Let me erase this. I'm gonna redraw this. I'm gonna redraw this anyway. So we have the two connected. But since the two connect, but there's no current on the right-hand transistor, so we basically can draw the equivalent circuit into this. Well, because the voltage O here is 0, so we got VO equal to, so this is VD2, VD1, plus sign is VO. So you look at it here, because this connected, so right away you can get VO equal to VD2 minus VD1. So therefore, we don't need a ground. Well, because it make us easier, and of course this is equivalent to GM times VID times RD. So, and you get the same gain. So eventually in the future, we will make this source a virtual ground. So even though the current source is there at the gate, because the two gates are connected, so for AC equivalent circuit analysis, we can assume like this one here is a virtual ground. That will make our calculation much easier. Okay, so that's how it's given in the book, and you can follow that process easily to find out what is the actual like the gain. Now we pretty much I didn't want to go through the large signal analysis, which is in the book. It's the section 9.1.3. You guys can go through that because that was very similar to the generic MOSFET calculations that we had before. But let's move on to the small signal operation where we have two inputs. So one at each gate. So because we now have experience of drawing the equivalent circuit from the previous slide, like here, you already drawn the circuit. So the difference between this one and the next one is that, well, the gate of Q2 is not grounded anymore. They both have a voltage source. But since we already concluded that there's a virtual ground at base, at the source, so it will make our equivalent circuit much easier. So in this case, we'll simply have we're going to have a virtual ground over here. And for the other side, we're going to have very exact identical circuit, which is ground. Well, in theory, these are connected, but we make them a virtual ground. Okay? So here to here is VG1, VG2 is the input. And here you have GM1 times VG1 and RD here, RD are there, and this GM2 times VG2, and this VD2, this VD1, from VD2 to VD1, we call VO. So since we make a virtual ground, so it's very easy to calculate VD1 and VD2. So we calculate VD2 is equal to minus GM times RD times VG2, and VD1 equal to minus GM1, GM2, RD times VG1. And then VO equal to VD2 minus VD1 equal to well, basically it's going to be GM1 times RD VG1 minus GM2 RD VG2. Now, this differential amplifier, the transistors are always identical. In theory, they can be a little bit different because of manufacturing, but they're designed to be identical. So which means you will have GM1 is always GM2. So once you have that one, we can further calculate VO equal to GM times RD, which is equal to VG1 minus VG2. So we got this really very important equation. So because the output is proportional to the difference between the input of G1 and G2, so that's why we call this differential amplifier. And the gain, we call it differential gain. Differential gain is going to be always called A, V equal to VO minus VG1 minus VG2 times equal to GM times RD, okay? So that's how we get the gain of the differential amplifier. In the future, for simplicity, in fact, we can connect the, later on you will see that the difference between the two inputs is what we amplified. So in theory, we can eliminate the ground. We can simply connect the two voltage sources together. So you can get, you can amplify the difference between these two voltage sources. In this particular example, is that we are going to have the input divided like by 2. So one on the input side, on output side. So basically what they're doing is really just saying, if I redraw the circuit like we have from the previous circuit, in this example is instead of connecting, so we'll simply connect like 2 voltage source. And it's like in the middle, there's a ground, right? But this 2 can be really just equivalent to 1 voltage, which is the difference between the 2 input. So that's what you have. Now, since we already verified that the source, the voltage source, the current source at the gate at the source can be considered as an open circuit, but we can have a virtual ground. So therefore, we derive this equivalent circuit over here. And since when we divide this voltage into 2 different one, and then we have one, each one is 1/2. So on one side, we'll have, and on the other side, we have minus VID over 2. So when you add these 2 input, you will get exact VID. So that's how you would be able to derive the gain. Once you get the half of the input and you add them together, you will get the same conclusion like what we had from the previous slide. We can also use that. We always use a pi model in this lecture today, but you can always use this T model. T model will make it a little bit easier because T model. The other day I illustrated how to convert a pi model into a T model, but when you have a T model equivalent circuit, it's very easy to calculate the different input and output voltages. For example, in this case, I will redraw the circuit. The reason I just want to redo the stuff so that we all understand what we are talking about. And in fact, if we use the T model, we don't need the virtual ground at all. This voltage is GM times V GS1, and this is GM times VG S2, and this is RD, this is RD, and this is the ground, and this is ground. And we have the input at here is VID over 2, and the input over here is VID over 2 and minus VID over 2. So you can see here, when we calculate VO, we can easily calculate this current, basically because the current is given, so we can calculate VD2 and VD1. So we can calculate VD2 easily because the current is flowing this way, right? So VD2 is equal to minus, like 0 minus RD times GM times VG S2. And VD1 equal to a minus RD times GM times VG S1. And VO equal to VD2 minus VD1, that's equal to RD times GM times VG S2 minus VG S1. And VG S2 minus S1 now, so we can plug in that, go to RD times GM. So VG S2 is 1/2 VID. VDS2 minus sign. I don't forget the minus sign. And minus 1/2 VID, which is positive. And you get positive RD times GM times VID. And we got AV is VO over VID. ID means input differentiative, GM times RD. So now, so use this, apparently, the T model, it makes it a little bit easier to calculate the gain of the differential amplifier. So you guys feel free to use this. But in this case, the particular advantage is that we don't need the virtual ground that we had in the previous when we use the pi model. So when we use the pi model, of course we didn't need it, but the virtual ground helped the calculation. You can in the future, if this, you can always what we call do this equivalent circuit analysis based on, like, sometimes instead of using the T model, just simply draw the small signal on the circuit not to replace the transistor. So this circuit is the same as the previous circuit, but instead we simply leave the transistor over there. But sometimes it's easier to imagine how the circuit works. The result is going to be the same, so we're not going to repeat it here. The other thing that make a difference that instead of having VG1 and VG2 equal to half of the input, here we simply have the input is connected to the ground. So because the circuit is symmetrical, so you can always put this into two halves. So 1/2 at G1 and 1/2 at G2. So you can easily calculate the output anyway. And half circuit, so like because this one, if you make it a half circuit, and this is the half circuit with input, but the most important thing again is, well, you have this virtual ground if you use this pi model. But if you use T model, apparently the virtual ground can be left, without a problem. So we can possibly, just as a sort of review, we can possibly draw the pi model and the T model in this case. So for the pi model, you have input coming in, and you have so the problem with T model is that, well, here, where does it go, right? So we make a virtual ground. So we make this one to work. And for pi model, that's for the pi model. And then for T model, we have this one here, and then we have this RD over here, and then we have ground over here. So, and over here we have this 1 over GM, and now we have VGS is over here, and this is GM times VGS. So the output over here, VO, and here, it doesn't matter where the bottom goes. We can always get VO equal to minus, and this VO equal to minus GM times RD times VGS. So that's how to do it. But in the previous circuit, because if we don't have the virtual ground, actually the circuit is slightly different. If we don't have the virtual ground, and here you're going to have really trouble to figure out. So this is it, and this is the ground, right? So if the current doesn't have way to flow, but eventually, the current has to go somewhere, right? So regardless of this, and in the future, you will see that, in fact, this is going to be some sort, maybe resistance, some sort of resistance for the high power. So, and it's the current source, and then this current source. So that's something we're going to deal with later on. But for now, let's just keep it like that. As the final example, we're going to have RL connected between them, because eventually, what's the purpose? You have voltage, yeah, you need to connect some load, and the load can be often a resistor, or like sometimes can be a current source as well. So in this example, we're going to start with with the current with a resistive load at the circuit. So to try to understand this how it works, then we just need to figure out the half circuit. So when we figure out this half circuit, it's fairly easy in the sense that we can figure out this. And here you have half VI comes this way, RD, RS, and this is, so that's your half circuit. And then the input can be common mode or differential mode, it doesn't matter. The difficult part is that how much is this thing to here? So in order to get the correct answer for the half circuit, we just need to do a little bit of analysis on the original circuit. So we know here is the current, is the current over here, we call it RO. If you look at the RO, we have RO equal to VO divided by RL. And if you remember previously, we had VO equal to VD1 minus VD2. And it's typically 1/2. And it's 1/2 just like VD1. Or it's going to be, it's usually 1/2 minus VD1 and a positive 1/2 VD2. So if we plug in this, no. I am making a mistake. So it should be the other way around. So basically, it takes 2 times VD2, also VD2, VD1. Okay, so 2 times VD2. So which means VD2 is equal to 1/2 VO, and VD1 equal to minus half VO. So if we plug in this one into the equation here, we have IO equal to VO over RL equal to VO is 2 times VD2 over RL, which equal to VD2 over RL over 2. So that's exactly what we need, which means we just need to break this one resistor into 2, and we can make this a ground, and this can be half of VL. So with this half VL, you will be able to calculate everything you need in the circuit. So that's fairly simple, how to get really the how to solve the circuit. If you draw the equivalent circuit, now you know that the equivalent circuit becomes, if we draw the T-model, we can get this T-model to work. It's this one here. RD is 1/2 RL over 2. Well, we use this as a ground. So let's make it a little better. So this is ground, this is ground, this half RL, and we have let's see how we draw this T-model. Yeah. So this is your output over here. VO, which is really VD1. And this is the current source, which is GM times half VID over 2 in this case. And here you have this 1 over GM, and then you have RS. And here, it doesn't matter, it goes to ground. So our VD1 equal to minus GM times half VID, and then times here you have RD in parallel with RL over 2. That's what you need to do. So once you find a VD1, you can either find VD2, and once you have VO, it's going to be your VD2 minus VD1, and VD2 is positive, we get to negative. So you got this is GM times VID over 2 times RD over RL over 2, and then times 2. So that 2 is canceling. You get your gain. So let me write down here. So the voltage gain is going to be GM times RD in parallel with RL over 2. So that's what we get for the example 2 is what we get. And of course, when we did this calculation, we are not considering that the RS is going to play a picture here. So basically what we did was, it's like this VGS is here. But if you look carefully, that VGS is between this one here. So let's make this clear. Because I did this like assuming that we know GM times VID times 2. But in fact, it's wrong, because this is not VGS. So this should be VGS. But the input here is going to be VID over 2. That's here. But what is VGS? This is RS over here. This is RS at the bottom. So VGS is this. Right? So if you need to get the actual correct, let me see, I have another graph. Yeah. So if you make need to make this correct, we need to really be careful, because now I actually have to redraw the circuit, because the previous calculation, I think I'll tell you that this is wrong. So now let me redraw the circuit. So that will make you understand better. So this is GM times VGS. And here is VID over 2. And here is R, what we call this? Yeah. So this is going to be the one that we're missing. So this is really 1 over GM. And this is RS. And we're going to connect this to ground. So if you look at VGS, so VGS is equal to what? Is to VID over 2 times the voltage divider, which is RS plus 1 over GM. So that's the only difference. So now your output VO is going to be VO. So here VO is going to be GM times VGS times RD in parallel with RL over 2. Now we replace VGS. So this becomes GM times RD in parallel with RL over 2. And then times VGS, and VGS is VID, and this is 1 over GM times RS plus 1 over GM plus 1 over GM. So and then we do a little bit of manipulation. We should be able to get this gain. So with GM, that's good. GM, so GM and GM cancel, and 2. So this, remember, this only, we should call this VD1 minus and minus. So this is minus GM times RD over RL over 2 divided by RS plus 1 over GM. And this is V2ID. And so VO is going to be VD2 minus VD1. And because VD2 is positive, so you can write VD2 equal to GM times the same thing here. So VO equal to VD2 minus VD1. And that 2 is gone. So you got GM times RD in parallel with RL over 2 divided by 1 over GM plus RS times VID. And here we got a voltage gain equal to no, that GM is cancelled actually. That GM cancelled with this GM. So there's no more GM. We need to remove the GM. So there's no more GM here. There's no GM here. So we got the gain is going to be RD in parallel with half R plus divided by 1 over GM plus RS. So that's your gain. I think with that, we're going to conclude the lecture, because I think we're already running over time. I'm going to come back to this at our next lecture. And how, if the load is not a resistant, but actually a current source, what will happen? So this is going to what we're going to discuss next lecture. Thank you.